linear lines for linear data sets, I can apply that process. If the data sets are not in the linear form, in that case, we go for a different technique called kernel trick. Kernel trick. What this kernel trick is? So many real world data sets are not linearly separable in the original input. So because in real world data examples, we can see that I can't draw a linear line to segregate the two different data sets or three different data sets, whatever may be. This means that the straight line or the flat plane cannot be perfectly divide this data sets or the classes. So what we are going to do, but here we are going to apply a kernel trick comes into one action. Kernel trick is implicitly maps the data from its original lower dimensional space into much higher dimension. So it converts the lower dimensional space into one higher dimensional space. That is called kernel trick. So in this view, what you're going to do it, we are going to transform the spaces. That the data that was previously in the non-linear form becomes linear form, linearly separable. So I'm converting a non-linearity to one linearity. This allows the SVM to find a linear separating hyperplane in an elevated dimension, effectively classifying the very complex and non-linear relationship without explicitly calculating the newer coordinates. So you can see in this graph. So these are the data points I have it. I want to draw the linear curve. Here the linear curve, when I'm going to draw it, that is not be a linear curve, somewhat like it may be in a U shape, or it may be in somewhat a bent curve. Like that, I'll be having a group of data. So what I'm going to do it, so I've drawn the plane. I have drawn the separation line, but the separation line is not in a linear form. Somewhat it may be a curve, or it may be inverted curve, or it may be in a new form, or it may be somewhat in a bent form. Like that, I can go for it. When I do that process, it is somewhat my cluster differentiation is not uniform, somewhat it is ununiform. So I want to make a clear thing. So in order to make a clear way of making my separation process, or I'm going to transform the space, uneven space into a lower dimensional space into one higher dimensional space. So what the kernel trick I use it. So what we are going to do it, I have a two sets of data classes. I start multiplying these two data sets classes, and I'll form a third one. That is A is one class and B is another class. I'm gone for a separation. So after doing it, I'll find out what is the value I'm going to get it for that point. The points, X points and Y point, I have it. So I've got the points. In the two table, I'm having it. In the third table, what I do, but in the kernel trick, I start multiplying A dot B. So when I start multiplying A dot B, I'll be getting a new data set. So when I plot this data sets on my graph, what I'll be having it, I find I'm converting. So the third column only gives the conversion of a lower dimensional into one higher dimensional space. So when I do that plotting, you can see that when I now if I draw a hyperplane or a plane or a line to segregate that points what I've got from my result. When I do it, I can able to see that my line is not a curved form. Instead of that, I'll get a linear way. So I'm converting a non-linear way, non-linear data sets into one linear data sets, so that this kernel trick, I'm using it to make this conversion. That is, two classes, I'm multiplying it, I'm getting a third quantity. That third quantity is nothing but product value. That product value will give a new dimension. That dimension, when I plot it on the graph, easily I can able to segregate for this different classes, so that again I'll apply whatever the rule I applied for my linear separable process. So same thing I'll do it for the further processing it, and I can able to make a proper prediction for my algorithm where I'm going to apply for different applications. This is the first one where we have a non-linearity condition. Next I'm going for what linear condition. This is what we call it as how I'm going to make it from a low dimension to one higher dimension, 2D to 3D. Like that, I'm going for a time. That is called new, especially we are calculating a new coordinates. So common kernel functions. There are different kernel functions that we use it. One is a linear kernel, radial bias function, polynomial kernel, and sigmoid kernel. Linear kernel is nothing but is an ideal for the data that is already in a linear separable form. It is the simplest, and it works under very high speed. Whereas a radial bias means, I told that inverted U. It is mainly used for the most popular and versatile kernel is highly effective for more complex or for non-linear data sets. So that is only I told that you'll get a separation curve in the form of U or inverted U, somewhat like a bend. So we call that curve is to be a radial curve. So this is only for mainly we apply for a non-linear data sets. The gamma parameter in the RBF controls the influence of individual training samples affecting the smoothness of the data decision boundary. Polynomial kernel is nothing but capturing the nonlinear relationship by creating a polynomial decision boundary. That is called the degree of the parameter. We say that x square, x3, x power 4, x power. The 2, 3 represents the degree of the polynomial. So, which controls the complexity of the curve, allowing the more flexible separations. Higher the polynomial degree will be, the better will be the outcome. Sigmoid kernel. Sigmoid kernel is nothing but, in spite, we have seen that by any neural networks activation function, this kernel can handle non-linear data and it's sometimes used in specific deep learning context for sigmoid. Sigmoid already we told that 1 divided by 1, 1 minus e to the power of y or x, whatever may be there. The x is nothing but the output what we get from the linear equations. So using that method also we can able to overcome the non-linearity conditions. What are the advantages of SVM and process? So advantages as, first one is high dimensional effectiveness, memory efficiency, robust to overfitting. Here you can avoid the overfitting process because we are going to have a maximization. We are going to do it on the marginal separations. So next is going to be memory efficiency. It is the subset training points in the decision function, which reduces the memory footprint. High dimensional effectiveness sets is nothing but, here we are going to say that the data sets with the numerous features such as geonomics data with the thousands of attributes I can handle in the case of SVM. These are some of the advantages. When you think about the disadvantages, scalability issues. So it can degrade performance can degrade the on very large scale data sets due to high dimensional intensity, SO of n square to O of n to the power of 3. So for higher scale and all, you'll have an this issues will be, you will be facing some issues in this case of SVM. Sensitivity to noises. It can be very sensitive to the noise data and overlapping clauses, as these points can directly influence the suppose what we call it as support vectors and margins. So as we go for a maximizing it, you can see that some problems, some of the points may not be comes under the case of analyzation process. That may causes noises in my prediction. Parameter training, sorry, tuning is nothing but choice of kernel function and its specific parameters. Example, degree for polynomial, gamma for RBF significantly impacts the model. So the degree or the gamma factor, whatever we choose it, that may also causes us a big disadvantages to the performance, where I have to go for careful tuning process to evaluate my prediction. Thank you. I think you'll understand this concept of SVM, where we have to apply what we have to apply. Real world application is nothing but, I can go for image classification, bioinformatics, text categorization, or any medical diagnosis. I can apply this SVM process, which is a powerful approach